Hello guys, welcome back. So in the previous video we saw about how the electric field would vary in the axial and the equatorial lines of an electric dipole. So now let's see how a dipole would behave in an external electric field. But the electric field must be uniform, and let's see why is that condition. So first of all, how do we generate a uniform electric field for this experiment? If you use a small charge, be it positive charge or a negative charge, the electric fields are going to be radially outward in this case and inward in this case. That is, electric fields are always radially outward for a positive unit and radially inward for a negative unit. Okay. So now if you consider, let's take any one of these diagrams so that you'll understand why this is not a uniform electric field. So let's take only this segment because it's symmetric, it can be looked upon in anywhere. So if you look at this part, this is how the electric field lines are. Close to the charge, the concentration of electric field lines are much more than if you draw the same unit over here. You can see over here 5 electric field lines are flowing, but over here only 3 are passing through that same area. So electric field at this point nearer to the charge is much greater than the electric field at the farther point. So this is why this is not a uniform electric field. A uniform electric field is ideally parallel to each other. That is, the electric field generated are in this way. This is how a uniform electric field would look. And now you can check this. Any unit of area you take, the same area in 2 either positions is going to have the same number of field lines passing through it. So that is why this is a uniform electric field. And how do you generate this? Either by an infinitely large positive charge or negative charge, so that the lines which emerge out are almost parallel. Even though they are radial in nature, but that parallel is more significant in their nature. Or else you can create it from even a charged sheet, a parallel charged sheet. If this is the sheet and you positively charge it, it's going to emit electric fields parallel to it in this direction. So now let's see how a dipole would behave. I'll draw the dipole in the electric field with a different color. Okay, so this is the field, and now the dipole can be oriented in any way. Okay, before we go to that, I'll just mention one more point, that is, by convention it is taken that the side from where the electric field emerges is the positive side. This side is the positive. And why is it? Because we have seen that positive charges emit electric field lines in the outward direction. So this is almost like thinking as if there was a positive charge here. So it emits in this direction. So the left hand side, or from where the electric field emerges, is the positive terminal. It's just for the sake of seeing how a charge would behave in a dipole. So this side is considered positive and this side is considered negative. Same logic can be applied here. If there was a negative charge, it would have attracted the field lines inward. So that's what's happening here. So left side here is positive and the right side is negative. Now let's place a dipole. A dipole can be placed in any orientation over here. You could place it either in this way, you could place it in perpendicular way, or you could place it at an angle. In these 2 cases we'll get the answer directly. But what if it was in this manner, or what if it was in this manner? In such cases you cannot find an answer easily. So what we are going to do is we are going to start with such a general situation where an angle is made, and then we can come to these conclusions by assuming the angles correspondingly. So let's first start with the general case of it having an angle theta with the electric field lines. Okay, so this is the dipole. I'm going to consider this side to be positively charged and this side to be negatively charged, and this is the center, and the center O has length L on either side, Okay, so what formulas do you need to be knowing over here is that the force, we have seen that the electric field at any point is the force ratio of the force experienced to the charge present. So from this we'll need the formula for force, that is force equals EQ. This is one formula that we require. And then, okay, let's see first how will this behave. So what do you think will happen to this dipole at any instant if you place it in this way? And let this angle be theta. Okay, so will the dipole rotate to the clockwise direction, or will it rotate in anti-clockwise direction, or will it move forward, backward, upward, down? What do you think is going to happen? So first let's draw the forces which are acting on this. This is a positively charged, and I told you that the right hand side or the arrowhead side is the negative charge, negative side of the electric field. Positive and negative attracts. So this is going to experience a force in this direction towards the negative side. And this is a negative charge, and left hand side is positively, it's considered positive. So again this is going to experience a force F2, F1. So these two forces are acting on dipoles, tending to pull away from each other. So for condition for a torque is the forces must be equal in magnitude. Are the forces equal in magnitude? This is the formula for force. F1 is the electric field at this point, E, times the charge, magnitude, which is Q. What about F2? F2 is electric field at this point, and this is why we require a uniform electric field, because electric field at any point is going to be equal. So electric field over here equals electric field over there. So it's the same electric field times the charge Q, because it's a dipole. A dipole has equal magnitudes of charges. So both the forces are equal. So the first condition of torque is satisfied. And the next condition of torque is that there must be a component of force which is perpendicular to the radius. That is, if you have lever, if you have a lever over here with the fulcrum so that you can rotate about it, if you pull a force in this way, there's going to be no effect on this seesaw. You can consider it to be a seesaw. If you try to pull the force, give a force in the direction like this, there's going to be no effect. But if you apply a force like this and another one like this, now it's going to move. That is, there must be at least one component of force, or one force, any force, that must be perpendicular to the line joining the radius. That is, they must be perpendicular to the dipole in this case. But here you can see this is not perpendicular, it makes some angle. So you're going to resolve the vectors. That is, you need a force in this direction. This is the force which is perpendicular to the dipole. So this is what we require. We need a force that is perpendicular to the, you can consider this to be the same seesaw. And you needed a force in the direction perpendicular to the seesaw. Same way you need a force perpendicular. So how do you resolve this F1 force in the perpendicular direction and the other one in the horizontal direction? This force have to be resolved into two components. And this is the component we require, and this one does not make any difference. This is similar to the force which you are pulling on the seesaw in this way. It does not bring about any change. And apart from that, the same way here you can do the same resolution of vectors and the other one. So these two forces being equal in magnitude will cancel off each other. So now, how do we find force F1? How do we find the component of force F1 in this direction? We have to it's just geometry. You have to find out the angle over here. So let's try to find the angle out. I'll draw a separate figure, triangle, so that you can see it better. This triangle, I'm going to start from this point. Consider this point and this point, okay? So it's in this way. (90°), that's the positive charge's end. This is the angle with theta, and this is the force F1. So we need to find this angle. We know this is theta, this is 90, so this angle must be 90 minus theta. How? Because sum of these three angles should be 180 degrees. So you can cross check, theta plus 90 minus theta plus 90 degrees equals 180 degrees. So yes, this is theta minus 90. And now we are going to consider this line is parallel to this line. It's in this way. This is the line we have, and this F1 is the line over here, and this is the line that is intersecting these two lines. So now we have to apply the alternate interior angle property. So we are given this angle, and this angle is always going to be correspondingly equal to this angle. That's the alternate interior formula. So 90 minus theta is the angle over here as well. So we got this angle. This is 90 minus theta. Then this is going to be theta, because these two vectors are perpendicular to each other. So we have all the angles we require now, and let's do the resolution of vectors. F1 has to be resolved along its horizontal component, that is cos. So this vector required going to be named as F dash. I'll use a different marker. F dash. F dash equals F1 cos of, what's the angle? 90 minus theta. We have to always consider the angle which is between the actual vector and the horizontal component for this case. So what's cos 90 minus theta? It's sine theta. So it is F1 sine theta. So this side's job is done. You don't actually need to calculate this, but if you do, you'll find out it is F1 cos theta. And now we have to find out this side, the force we require, F dash, same in magnitude, right? So F dash over here is again F2 into, you'll find out to be the same process because it's again symmetrical. So you'll get it as F2 sine theta. F1 and F2 are the same, so together you can call them as F sine theta. Both of them are equal to F sine theta. So now we can go ahead with the derivation. We require this for applying the direct formula. So now we are going to apply the formula for torque. The torque at this point at the center is the sum of the individual torques due to the either ends. So the torque, let me just rub this diagram off, and I'll start from this side. Okay, so we have found out both the force F, let me name them F dash. Okay, so F dash equals F sine theta, which is, we know that F is equal to E times Q. So I'm going to rewrite this as EQ sine theta. So this is the equation for both the forces having the same magnitude. So torque 2 is R cross F. That is the force cross the radius to the center of rotation times sine theta, because it's a scalar vector product. So RF sine theta, where do not confuse this sine theta with this one. This theta we have assumed is the angle between the dipole and the electric field. But over here the formula sine theta is the angle between these two vectors. Or else let me name this one as sine phi. RF sine phi, where phi is the angle between R and F. What is the angle between R and F? Well, R in this case is LF, okay? LF sine phi. It's 90 degrees. So sine phi is sine 90, that is equal to 1. So this is the torque LF due to this side, side 1, and this is side 2. So what is torque 2? Again it is R cross F, and the same procedure, RF sine phi, and phi is again 90 degrees. So you get LF, where L is the distance between the force acting and the center of rotation. So we got these two torques. You just have to add them. The total torque of the system, torque toe of the system, is 2LF. This is the torque. Now you just have to substitute the formula for F, which we have found out. F dash, the force which is perpendicular. So the torque of the system is 2 times L EQ sine theta. We just have to group some terms, just like how we do it in the previous derivation. 2LQ E sine theta, and 2LQ is a dipole moment. So you get PE sine theta. This is the torque acting on the system. You can again simplify this, not simplify but denote it in a different way, that is torque toe equals P cross E. This is the cross product, a vector product. So P cross E is PE sine theta, just like how R cross F is RF sine theta. So this is the torque due to a dipole in a uniform electric field. This torque is going to cause the dipole to rotate. Now let's consider those cases. I'll write the two necessary formulas and I'll draw the next diagram. Okay, these are the formulas we require. That is torque, total torque is PE sine theta. Now we are going to consider two different cases in which the electric field is perpendicular to the dipole, and the other case in which the electric field is parallel to the dipole. So let's see what happens in either of these cases. In this case, the angle which the dipole makes with the electric field is 90 degrees. So sine 90, torque toe equals PE. This is the maximum value that the dipole can experience when it rotates. That is, when it is perpendicular to the field. In this case, the theta can either be 180 degrees or 0 degrees. How is it 180 or 0? Because you can consider it to be plus minus or minus plus. So both these orientations have the same effect, but in one case the angle made is 180, that is completely in line, and the other case is the opposite, which is 0 degrees. So it doesn't make a difference because cos sine 180 and sine 0 is 0. So that's the whole point. So torque in this case is 0 degrees or 0 newtons per meter. Unit of torque is RF, that is Newton meter. 0 Newton meters and this much. This is the minimum case and this is the maximum case, and you can get that from this formula. So if we started off the derivation with this, we could have easily concluded, but we cannot find out for any general case, and that is why we went with the derivation. So this is the torque acting on the system. And how does the question might be asked, that is, if the torque acting on the system is 0 in this part, then how come the torque continues to rotate if it has to come to this point at least once? That is, if you have a torque, a dipole, it has to rotate, and when it is rotating, at one point or the other, it has to come to this orientation where it is parallel to the field. So first it's going to be in this way, and then it's going to rotate and it has to come to this point, right? So if the torque in the situation is 0, how does it proceed to rotate? The answer is because of inertia. So once it reaches to this point, it still has that little bit of velocity to push it a little further that is a minute amount it is being pushed by. So once it moves out of this angle, now the further torque can be applied in the just like how we discussed. So the role that inertia plays is to act as an initiator when it comes to this position, and then the cycle continues again. The next turn it comes around, again inertia acts, pushes it a little forward, then this continues by itself. So this is how a dipole behaves in a uniform electric field. And then there's only one more topic in this chapter, that is Gauss Theorem, and there's 4 applications which are just small derivations. So thank you, I'll see you in the next video.